Merry Symposium Day. Um, Today we're going to look at executable versus declarative encodings. Well, that sounds like a mouthful if you haven't heard of these words before, but we're going to get all into it. And as an example, we're going to use the medium complexity domain of parsing. So we're going to build a parser first in an executable format and then in a declarative format to sort of be able to use one domain and get a sense of what these encodings look like and allow you to do differently. And so, yeah, any words at the start about just what does this mean, Adam? Executive, like what is the idea of an encoding anyway? What are we encoding here?
Yeah, so I think this is hopefully going to be a nice session because I think we've hit on these ideas indirectly a couple of times before, like particularly when we did the Zio from Scratch series, but it was always a little bit in passing versus the main topic. So hopefully this can be a good resource if you're like, hey, what's the deal with this thing? And basically it's well, how we encode, how we write our programs. And in a way we have to, I think about the declarative one requires more thinking because that's less what we do every day. Of the executable, you could kind of think about as you don't think about it because it's what you do all the time. If I tell you to implement merge sort, you're going to actually go and you're going to like take an array and you're going to write a bunch of code that's going to swap indices around for elements until the array is sorted. And then you're going to like look at the array, and when you're done, the array is going to be sorted. And that's going to be like, okay, we did the thing. And that's almost so common for most things we do that we don't even really think about it. Versus a declarative encoding is separating the description of what we want to do from how we want to do it. And so like in that simple domain, you could almost imagine someone says, well, go implement merge sort. And you say, okay, case class merge sort, thing to be sorted. And then you don't do anything else. Like you're just, okay, that's a description of what it means to like merge sort something. And like most of the time we don't think about that because it's like, so like, it's so lazy in both the functional terms and the actual functionality we're providing of like, we haven't done anything yet, that like, we don't think about it. But you could imagine then you have kind of the interpreter that you implement for your merge sort algorithm that says like, okay, I got this array, I'm supposed to merge sort it. Okay, now I'm going to do all these indices. And so another maybe more familiar domain you could think about this in would be Spark, which isn't purely functional, but has a similar little bit of a separation of you describe all these operations on these RDDs, these resilient distributed data sets. But as you're describing the operations, nothing's actually happening. You're just building this kind of description of these operations you want to perform. And then when you actually go to like execute them, then things start flying around across the network and it starts actually doing what you asked it to do. So that's the fundamental distinction of executable is I'm doing it right now. Like as I tell you what I'm doing, I'm actually doing it. As we're talking about running, I'm like shoes on, we're going out the door and we're chatting while we're jogging, versus declarative is like, we're just making a plan. We're sitting on the couch, we're saying like, okay, we're gonna jog here, then we're going here, then we're gonna come back home.
Okay, awesome. So with that in mind, let us begin with a slightly simpler example than Spark, which is parsing, which will sort of also, I guess, be a bonus lesson if you've never written a parser before. We're going to make a relatively simple one. We'll see how complex we can make it. But the idea is of a parser, right, that you are taking generally a string that is hopefully representing some type of structure, perhaps a list of coordinates or maybe just a single coordinate, and you want to parse that into something with more structure, because a string can really be anything, right? It can be a bunch of nonsense characters. You're trying to extract a very particular structure from something which is inherently less structured and turn it into something maybe like this. So X int, Y int. So this This would be the string representation. This would be the Scala representation. We need a way of translating from one to the other. And that is something that you could use a parser for, right? So if you have JSON, you could parse it into maybe a type-safe JSON representation or a Scala-fied JSON representation or something like this. So we want to go from this into 10.2. Obviously, because of the chance that it's might be nonsense and cannot be parsed into a coordinate, we have to this either blow up or use the beautiful functional way of making all functions total in Scala, which is if it doesn't work, return none, otherwise return an option. Sorry, a sum of this. So that is going to basically be the interface for our parser, and we'll take a look at this right now. So we're going to have parser, and it's going to have a method called parse on it, which is going to take some input, which is going to be a string, and return an option of some output type, which is going to actually be a parameter, which gives this parser a good deal of power. The one problem, though, is that we want this parser to be composable, which is a good thing. We would like to maybe have a parser of just ints and write something maybe like this. So parser examples. So here's the code that we wish to be able to write at the end of the day. And the nice thing is we can actually share this program and probably copy paste it over to the declarative interface, maybe with a couple of changes. Because this is an encoding, it's not necessarily how you use it. Though which encoding you choose does maybe give you some powers that you may not have in one or the other. So we might want to have ourselves an int parser. And maybe we'll have something that's just eventually parser.int. And we'll create an object parser, top level here. And we can add this value int in here, which will be, we don't know how we're going to implement it at all yet, but it's going to be a parser of it. So it's going to take strings and get us back potentially integers. And so if we want to make ourselves a chord parser, so a parser of chord, we would like to do something like the following. We'd say parser.int, maybe we can use a for comprehension or something. There are many ways of doing this. So something that we want to eventually have, like before we worry about the encoding, what's the language going to look like? We first want to parse out, if we look at our example, like an opening parenthesis, an int, a comma, a space, another int, and then a closing parenthesis. So we could do something like parser.char and give it an opening parenthesis. Then we can do parser.string maybe, and comma space, where we can be flexible about this in the future, but for now, this, and then we can have our closing parenthesis. And we can bind these values out. So now we can return a chord of X and Y. Obviously, this does not compile yet, but that's the idea. So we make these small parsers that do one thing, and then we can use them in multiple ways. And you might be able to sort of eventually have a list of chords parser, which would parse a list of coordinates. And that could be as simple as one common method combinator on these things would be taking another parser and saying like rep for repetitions, or separated by, and then maybe we could do comma space, another parser.string of comma space. So now we can read a whole list of chords that should be separated by a comma and space. So the point is, we can define these individual parsers and sort of slowly build them up into more complicated parsers, which then we can reuse, and so on and so forth. And the reason why this is important to talk about now, besides getting a handle on what we expect these to look like, is, and let me maybe actually also create these methods for now. So if we take a car, we want this to be a parser of a car. And if we take a string, we want this to be a parser of a string. Okay, there we go. So everything is sort of compiling. For comprehensions to work, you need two more functions. And it can actually, if you hit Option Enter, it will prompt you to define these. So we need a flat map and a map, absolutely, which basically will take the value that this parser parsed and call a function on it, getting another parser, which will eventually return that second parser. And map does the same thing, except just from A to B. There's no nested parser. Now that we have these methods, everything except, separated by. I can do this as well. This would take another parser, parser of really anything. We don't care what it's a parser of, because we're not using the result, and we're going to get back a list of A's. Cool. And there we are. So now everything is compiling, despite the fact that it's obviously broken and not going to work. Okay, so we'll fill that stuff in momentarily. The important thing, though, is there's one problem with this sort of main method, this parse method, which is going to be the bit that defines a parser. This is going to be implemented maybe differently. We're not going to have it defined up here. And the way this is going to work is we're going to try to parse some inputs, and we might fail or succeed. But let's take a look at our example up here. If we first run this parser car of just the opening parenthesis, and we succeed, then when we try to parse the int, we need to begin parsing, not at the beginning again, but at the 10, right? We've successfully parsed our opening parenthesis, and we wish to sort of peel that off the front and keep going from there. And if at any point we fail to parse that next bit, like say it did happen to start with a parenthesis, but it was just a bunch of parentheses and not a coordinate at all, then we want it to fail at that point. But if we do succeed, we want to sort of consume what we've parsed so far until we parse everything. And then at the end, we can return that value successfully. So in order to facilitate that, we need one bit of information here as well, which is instead of just right now, we sort of have success or failure of a single thing that we've parsed, but we wouldn't be able to, with this signature, parse anything more than a single character, a single int or something, or we wouldn't be able to compose these. We need this concept of a remainder. So we can actually have both the value that we parsed as well as the remaining string. Hopefully that makes sense. And this is going to allow us to, in our implementations, thread the remainder that we have not yet parsed through to the next parser. And that's, yeah, and that's that. Okay, any other thoughts so far, Adam?
No, I think that covers it pretty well. I think one thing we'll come back to a little bit when we do the declarative encoding is just this fact that we're returning the string here. We could think of as a little bit of a implementation leak. We need it in this executable encoding because we want to be able to run one parser and then run another one after it. And we need to kind of know where we are. So we either need the new string or potentially have some index that tracks where we are here. But from like the end user perspective, it's almost a little bit of a leak of really like from their perspective, they just want this A here or the non-case indicating failure, or maybe that becomes an either that has some kind of failure message. This is really only for us here internally. And the fact that we have to expose this as part of our API is a little bit of previewing one of the downsides of this more executable approach.
I suppose it would potentially be possible to do something like this, right, where we first call parse on the inputs and then map over the option to just pluck out the result, which could be a nicer
right. And we could do something like make this like private here or something. Yeah, there are ways you can kind of get around it.
Oh yeah, we will see it more elegant. Yeah.
Yeah.
But I'll keep these both public for now.
Yeah, exactly.
Okay, so now to the actual encoding bit. We haven't really written anything yet that is an actual parser. We've sort of built out some stubs and some general types that allowed us to stub out a potential implementation of potential usage of the parser, but we haven't written anything that touches the input or returns a result. And so now we're going to start with that here. And I think one of the more, there are many fundamental operators that we could choose, but let's just select car for now and start with this. This is quite simple, right? A parser is going to take a string, and this is going to parse out maybe a a single character from that string, returning the rest of it if it matches this character. So to do this, we just make a new parser, a parser of car, and it's going to implement this, give us a stub here, this parse method. And what we're going to do is check to see, if inputs, well, I guess we should do this, right? Input.head option, because it might be an empty input, in which case, well, we can't parse a car off of it, and we should fail. So if the head, the first car, is equal to this car we're trying to parse, then great. We can return our result, which is a tuple of that car as well as the remainder, which would be input.drop1. So drop the head of this. And then I guess I think I could also do input.tail in this case, because there is a head. If there's a head, his tail is partial and it will blow up in some cases, but not in this case. And then in any other case, we'll just return none. So whether or not the head didn't exist, or if the head did not match the given character. And we could even use the single abstract method syntax if we wanted to. I'm going to take it back. It's kind of always annoying if you want to then add a second method. For now, I'll keep it like this, so we can really see this essence of executable encoding, which is we are building the thing sort of as its implementation is what it is, right? It is just the function, right? It's this executable thing. It's really just a method in this case. It's not a description. It is the thing that it's going to do. And it's anonymous. Yeah. It's just it's a new instance of this parser trait that's going to parse a single character.
And one of the advantages of this is I think it's more straightforward to do when you're getting started, especially if you're not familiar with the other encoding. But I think just in general, this can be easier if you just need to do something quickly, because you get to really focus on just one part of your logic at the time. Like here, when we implement car, like we don't really know anything about how we compose these parsers. We don't know anything about this other parser. We just got this like pretty straightforward problem that this method signature here like tells me to solve of like, okay, you got a string, either give an option that has some value and a remainder, or give none. Like we don't have to think about anything else. We just get to do that one thing.
Yep. And then this one is super simple. We're just going to check for a string. If it starts with the string, then we're going to return the string, and we're going to drop from the head the length of the string to get the remainder after that point. So that's string, that's car. Int could be a little trickier, actually. Now that I think about it, in fact, maybe in order to simplify things a little bit, we can just make a coordinate take not integers, but just strings, or maybe let me think. Okay, we'll do ints, but we'll keep it very simple. It'll be a single int. This because we want to be able to sort of switch between the executable and the declarative encoding sooner than later, and not spend the whole time working on parsers. So this will only parse out a 1 or an 8 or a 9 instead of maybe a longer int, which we can implement, but it'll just be a tad more complex. So we'll make a new parser of ints, and what we can do here is actually, what could we do? So we could make a new parser with ints. So there are two things we could do, or we can use a more fundamental parser like the car, or like a oh no, because we don't have one that's match anything. So let me do this instead. So I'm going to say do any car, which is going to get us a character. If it still fail, but basically if it exists, if there is a head, then that's what we parse out. Otherwise, nothing. We don't care what the character is, so it can match anything. So now that we have any car, we can say any car, and then we can try to parse out an int. Now we might fail. So this is a little interesting, right? We could, let's see, we could use flat map here. Yeah, we haven't built that many other combinators. So let's say, okay, so we're gonna get some character. And now I guess we have to return a new parser of int. And so it's kind of silly in this case because we're going to ignore the input. Oh, no, we're not. So we're going to see if, okay, we could do car dots toString dot toInt option. and then match on this result. If we got an int back, we can do sum int, and then the remainder. And then otherwise none. I hope this works. I may have taken too much of a shortcut. Let's test it out real quick, because I'm skeptical of myself here. So I'm going to make a main function. I'm going to say parser dot int, and I'm going to say parse 12. So it should parse the 1, and we should have back as the remainder the 2, if it works. And I should probably print the result out.
We don't have flat map here, right?
Oh, that's true. We did not implement flat map. So hey, that's good.
It's a good opportunity to
Yeah, we have to implement the actual
go back and
list
do
parser.
that.
So what does it mean to flat map? So we need to make a new parser of B, which is nice. And here, let me implement the this thing will automatically generate.
Lovely.
And so yeah, let's think through this. We need to return an option of a B and a string. But first, remember we're inside of another parser. And what we tend to do sort of habitually is when we have a trait, we do this little self thing up here, which lets us rename this in the scope of the parser. And that is because when we make these nested traits, this no longer refers to the outer parser, the parser that we're chaining flat map on. Instead, this would refer to this new parser in here. So in order to maintain a handle on the outer trait, sort of the root trait, we write self here to rename it, to alias it. So now we can refer to ourselves here. And the way this new parser is going to work is first, it's going to try to parse the input with the original parser. And then based on the result of that, it's then going to, if it gets the A back, if it gets a none back, there's nothing it can do, because the only way it can ever get a parser of B is with an A. So if it gets a none, we have to return the none, which is totally valid. But if we get the A, then we can call our function with the A, getting back a parser of B, which we can then call parse with the, oh, sorry. What do we get back? We don't get back an option of B, we get back an option of a tuple. So, sorry, f of A, and then we can match, wait a sec. Oh no, so sorry, parser, then we parse with the, oh, wait a sec, A string. Okay, so there's the A, and then there's the remainder, the remaining input. So we call this function with the A, and then we parse it with the remaining inputs. And then we get back our result. So it's actually kind of straightforward there, a little tricky maybe. Okay, and now we should have enough to at least run this int parser. Oh, no, still sad. Main predef question mark, question mark, question mark.
Oh, we're using succeed and map here. I think that's our issue.
Okay, so succeed should be pretty easy, yeah.
Mm-hmm.
A new parser of A. And here, let me just do this thing just so it autofills.
Yep. So this is a parser that just doesn't actually take any of the input, but just succeeds with this value. So this one's going to be super simple because we're just going to succeed with that value. And then we're just going to return the input unchanged because we haven't consumed any of it. And
nice. And then separated by, I'm going to comment. Is it going to get angry at me if it, oh, because I am calling separated by. I'm just going to comment this out so it doesn't blow up. And I'll keep it unimplemented, but I won't try to actually execute that line of code. Good, good. Okay, so yeah, we have a 1 and 2. So I did implement it correctly. Huzzah. So now that we have implemented flat map, we know that it's going to execute the first parser and then call the second parser with the remaining input. So that's why we didn't have to, we could just pass the input along wholesale because we didn't care about anything. Now there would be maybe a nicer method that we could use to implement this because it was kind of awkward to write a whole other parser in here. Something like map or fail might be a nicer way of doing it, where we just return an option of the result. But we're just going to keep it at this level for now. Okay, so yeah, it seems to be working here. So I guess, yeah, let's try to run our chord parser then. So chord parser dot parse, and then I can do some kind of chord. So H3, and I think I had the yeah, the comma space. So does this work? Hopefully it does. It does. We got a sum
Very
of
cool.
3 and so on. And yeah, we won't do separated by for now. But yeah, that's kind of the idea of parsers, of these parser combinators, as they're called. However, we used this executable encoding, which means that we basically had a trait that had a method that we left unimplemented. And then inside, we define these parsers by basically creating these new executable variants, these many basically wrappers for functions, essentially, that sort of were what they did. They weren't quite descriptions. You can't really introspect them. You can't really optimize them. They are just this, they're a parser of something. You know, they're going to parse that value out maybe, but you don't really get to know anything else about them. And it can be a little awkward at times, right? Especially the way I sort of wrote some of this here. You can still, you know, reuse other primitive parsers. You don't have to sort of re-implement everything as a new parser, and that can make it nicer. So some of these higher level combinators might actually look identical between the declarative and the executable encodings, just because neither of them touch the fundamental operators, and they're all just in a higher level language. If I didn't make that nap or fail a method, then this one could not have to implement a new parser at all. But yeah, that's kind of the executable encoding. And it's pretty straightforward and easy to get started with, but it's not the only way of doing things. So maybe we could grab this example, what we have so far, and before we go any further along, we can maybe copy everything to this declarative package and then delete most of what doesn't make sense anymore. So let me get this out of the way. So we have ourselves a parser. We're going to, we can keep the methods that sort of do stuff just in terms of other things. So map here doesn't define anything itself. String, we're going to get rid of this. We're going to get rid of car. We're going to get rid of any car. We're going to get rid of int. And we're going to get rid of succeed. And I think, is that it? Yeah, I think so. I think now we have the object and we can keep this same implementation, despite the fact, once again, it's not going to work. And let me force all to follow me. So yeah, now we're in just the declarative file. Adam, if you wanted to, oh, there's, yes. Yeah, so there is one question, which is, would a type class approach be considered an executable encoding too?
A type class would typically be an executable encoding. You could potentially imagine a type class that would be more declarative, but typically when you have a type class and it's describing something, you're actually doing that thing. Though really, I think a lot of times you can think about a type class as being a little bit agnostic over the type of encoding. I don't want to take us kind of too far off topic here, but if you have something like, let's say I have trait associative A, and so this is going to define some kind of combining operation that's going to take a left and a right. So this is just describing like the concept of combining two things. And depending on how I implement this for particular type classes, this may be either executable or declarative. So for example, if I do, so if I say int associative, it's going to be a new associative way of combining integers. And here my combine is just going to be left plus right. This is a executable implementation of a combining operation. But let's think about something else. So let's say, well, let me just make my own little final case class number. Maybe I'll make it a seal trait actually.
Should we potentially show off maybe the parsing version of the declarative first? I mean, maybe not, just because like this is, I think it's a clear example that like this associative instance of a type class is totally the same pattern that we followed for the executable encoding. But if we're going to show off one that's declarative, maybe it'll be nice to show off first in the parser example.
Sure, we can come back to this after we spend more time on this. But basically, I think the high level answer is that a type class implementation, a type class itself is somewhat agnostic about whether its encoding is declarative or executable, and particular implementations of that type class or of that abstraction could do so in a way that is executable or declarative.
Yeah, we should definitely return to that.
Yes.
But so yeah, did you want to show some maybe up at line 7, right? So what should change about
Yeah.
this?
Yeah.
I deleted most of the implementations, but what do we need to do to make this declarative now?
Yeah, so going back to that idea of kind of advantages and disadvantages. So advantage of the executable was it was pretty simple and straightforward. If we just, in each place, we could locally implement our logic. But the disadvantage was that because our logic was local in each place, anytime we had some information that we wanted to pass around between different things, we had to do that really explicitly. And so we saw that with like this parse method here, where like every time the parser has to return the string of the remainder. And you could imagine if we had other state that we wanted to work with, if we wanted to say, well, like a lot of times in parsing, you'll have an operation that says like, ignore this, like you don't need to capture the input of this part of it. I just want you to parse it because I want you to get to the thing I actually want to parse. Like in our example down here, we like we make sure there was a opening parentheses here, but we didn't actually want to do anything with it. And so a lot of times these parsing libraries will have a separate operator to say like, I want to parse, but just discard those things. And if we wanted to add that here, we'd have to add like yet another thing we're returning here that says like, well, are we in the region where we're discarding or not? And so the disadvantage of this is that our state gets scattered around all these different operators and we have to explicitly pass it around. So to go from an executive to, or an executable to a declarative, we'll probably get rid of this one here. And we can still, maybe we'll just call this parse now. And versus in the previous one, we left that abstract and we implemented it in these different cases down here. Here, we're ultimately going to actually implement it probably here. Sometimes you'll see these methods that actually run the thing in like an object or somewhere else. And sometimes you'll see these being called either the executor or the interpreter of this description. But then what we're going to do is each of our operations here, at least our primitive ones, instead of doing something like we were doing down here before, we're just going to create new data types for them. So this parser thing is going to become a seal trait because it's only going to have these specific primitives that we're going to implement here. And we're just going to create some primitives for ourselves. So probably a very simple one is we'll have this one that we can call succeed. And this will just take an A and it'll have an A inside it. And it'll extend parser of A. And so at least this part of the declarative encoding ends up being really simple because all of these implementations become almost trivial, where like the implementation of this seed parser is just succeed of A. And the implementation of this car parser is just, what do we call it? We called it car parser. Okay, car parser of C. Yeah. And the implementation of string parser is string parser of string.
Mhm. And I guess I can
And
a case object for any car as well, which should extend, and we can probably simplify this later, obviously, but for now.
yep, and we're
so-
going to need one more here for this flat map thing. And this is probably the one that's the most complex of these. And so we've got to think of like each of these is like instructions in this little language we're building up. And so it's got to have all the information to instruct us when we go to run this thing of what we want to actually do. And so like here, this flat map one is going to need to have the current parser inside it. And then it's going to have this function that we want to execute. And so we can go down here and, oh, excellent. It's already one step ahead. Okay. And so now this should actually, I think, all be compiling now, with the exception of us having, oh, we need the int parser here. Int parser, what do we call it? Oh, we don't have the int parser yet. Okay, well, we'll make int parser.
I got it. And parser.
Yep.
Yes.
Yep. And so we're already seeing another one of the both advantages and disadvantages of the declarative encoding here. So we can see it's already pushing us much more to really think about what the primitives are in this parsing language that we're creating. So in the executable encoding, there wasn't really that much of a distinction between a primitive and a non-primitive. I mean, we could kind of say, okay, are we implementing new car or not? But from the actual perspective of the code we're writing, it wasn't that much different. Like, it's still the same method. It's just exactly what's in the body of the implementation of that method. And in a way, that's like nice when we're getting started, because it's very flexible of like, anytime I need to, I can always drop down to that level of just new parser and kind of implement that parse method. And I can just always use that to like solve my problems as I'm doing things. Versus here, every time I want to create a new primitive, I've got to do a little more legwork of I've got to both create this data type and then call the data type. And then we're going to see I'm actually going to have to like somewhere I'm going to have to pattern match against all these data types and handle them. And so there's a lot more of a conceptual cost to adding more primitives. And so you really have to think about like, what are the primitives here? Like here, you might wonder like, is any car really primitive, or is that like a combination of some other set of parsers, or right, is that somehow derived from the car parser? And ultimately, I think that's usually like a good thing, at least if you have kind of APIs that you're going to be using for a long time, because you end up pushing like all the tricky logic into the interpretation of these things. And then you have a lot of higher level operators built in terms of them that are a lot more simple. And so I think your code ends up becoming more maintainable and has fewer bugs over time, but it probably requires more work up front to figure out what those primitives are.
Yeah, it can be good to feel the pain, right? If the pain is meaningful, you want to feel it. With the other version, it was muted, right? It was just like, yeah, you're feeling weird, so you take a bunch of Advil, and then maybe you should have gone to the hospital, but you won't know it. In this case, you're gonna feel good pain, which is that if you're creating way too many primitives, it's gonna just be annoying to type, and it's gonna look weird. Yeah, like in the other place, I knew because I'd written the declarative parser enough that we were doing unnecessary things, but like you could easily like, what's wrong with this? We need all these methods. We're making all these parsers. So be it. That's the only way to do it. With this, it makes it very clear that you have this sort of minimal subset of primitives, and you want to keep these minimal and orthogonal, and yeah, we'll keep it at that for now. But awesome.
Yeah. So now we've got all these data types, but we've done like the lazy part. It's kind of like when we talked at the very beginning of like, we've got like, okay, does data type like merge sort this thing, but we haven't actually done the merge sort. We've just described it. And so now we've got to actually do that. And so I think up here, we'll just do this in this parse method, and we'll end up just essentially matching against these things. But one of the interesting things about the declarative encoding here is that we separate that out a little bit. So I think I'm going to have the parse method here just because it's a convenient place in the API. But in this world, there's no requirement that the parse method be here at all. I could have some completely new method, right? I could say this is good. This is going to be a new module, my custom parser, and it's going to have its own method, parse custom, that's going to take a parser. It's a parser of A and a string. That's a string, and it's going to give me an option of A. And I'm just going to implement this by matching against the parser and doing some stuff. And I can either put it here or I can put it inside. And in fact, I could have different ways of interpreting this parser. In this particular world, I'm not sure it's going to be that important for us to have different ways to interpret this parser, but we could imagine, like, if we were describing some kind of operations in different data sets, maybe there's one way we interpret it where we just do it all like locally in memory, and there's another way we interpret it where we like shard it out to a bunch of different nodes and we do all sorts of distributed computing between them. So that separation between description and execution gives us more flexibility, where then we can choose to execute that description in different ways.
The executable encoding is opaque, right? It's this jelly blob of active volatile energy that's just doing its thing. It is the thing that it does, and it's nothing else. And you just kind of throw it, and it does the one thing it can do. Whereas this is just a description, motorcycle, and you can do you can interpret it different ways. Awesome. Maybe I'll save this. I'll move it to the bottom of the file.
Yeah, perfect. All right. So meanwhile, I'm going to go back. I'm going to implement this parse method. It's going to take a string input, and it's going to give me some output. And so generally at the highest level, what we're always going to want to do in this interpretation is we're going to look at these different cases we have, and we're going to actually execute them. So we could almost imagine that, like, we've written this little like program stack and like a very old school like imperative style program of each of these is like print something out, go to this line, do this thing. And now we're just implementing we're just like the computer that's just going to go through and just follow each of those instructions. And the cool thing about this is that because this is a method that we're implementing, we can do anything we want in here. And in particular, we can maintain whatever state we want to maintain in here. So like, whereas before we had to like explicitly pass around this like remainder, and like that had to be like the return value of each of these functions, like here, if we want to, we can just say current string, right? And we can do all sorts of mutable stuff in here, because this is just, we're doing it internally. Like, as long as we just create mutable things internally and we turn them into immutable things by the time we're done, this is still going to be a referentially transparent function. So we could just say current string is going to be the input, and every time we do one of these operations, if we need to change what the current string is that we're working on, we can just do that. And if we decide, well, we actually don't want to change the string, we just want to change the current index we're looking at in the string, we could do that as well. And we don't even have to change any of our method signatures, because all we're doing is we're optimizing our internal implementation here.
So I'm just going to make that remainder for consistency with the other one for people who want to look at it later.
Yeah, I think that is fantastic. And so here, like, let's start working through how some of these would be interpreted. So if we've got a parser succeed A, then our life is really easy. We can just say sum A, and there's nothing else we need to do. Let's then, and sometimes here it can also be good. Oops, sorry, I think I'm accidentally deleting your stuff. Sometimes it can be good just to give ourselves like a little more space here, because these can be like what you end up doing here is you put a lot of your logic here. So this is going to be like a big method by the time we're done with it, where we're going to essentially take a lot of the logic that we already implemented in the executable encoding, and we can actually pull it in here and use it in this declarative encoding in this interpreter. So like if we want to look at any car, and we go back, and I'll just grab the any car implementation we had before. So what we were doing is we were getting the head option of the input, and we were matching on it. And so we can do something pretty similar here, I think, of this time we'll just have this remainder be the state we're working with. So we can match on the head option the remainder. And then there we go. It's already got what we need here.
But I guess now we don't need this remainder bit.
Well, and now we need to do something a little bit more imperative, assuming we're going with this var remainder equals input, because now we just need to say remainder equals remainder dot tail here. And right now this is going to be a little bit less important because we haven't gotten the cases where we're doing another parser after this one, but setting ourselves up for this, we want to say, okay, if we've used this input, then we got to go on to the rest of it.
There is also, I think, here the chance that, well, I think Scholars gets a little confused sometimes. That's the one downside of these declarative encodings, just because of all the types in here. It knows that we want to go and return an A from this, right? But this is a car, because this car is not an A, and therefore that doesn't really make any sense. So we might need to cast this as an A, but also actually, Adam, do we need to store our current result in this case? Because it does look like we're not currently sort of recursing. So it looks like we might need to.
We're definitely going to need to do more looping. Yeah, we're kind of handling the very simple cases where we only have this parser, and it's really not until we get to the flat map case where we're going to get to the case of like we have more parsing to do.
Okay. Cool. So yeah, let's wait until we get there for the funness. But things sticking in your craw that you're like, how is this going to continue? Well, we're going to have to change a couple things, but we'll work up to there.
Yep. So let's do a few more of these parsers, and I think we can again kind of leverage the previous logic we have. So like, let's see.
Oh, well, this one's interesting because it's also calling into flat maps, so that might be fun.
Yeah, so that may be a good one to, yeah, that may be a good one to say we don't want to actually have that be primitive.
Yeah.
So yeah, maybe we take that out of here and we kind of, we'll put a question mark there for the implementation.
Map or fail, this operator called map or fail is what we can do. I will copy any car though. Oh, we have any car. I will copy car parser.
Okay, and I'll do string parser. String parser. Yep. That was string parser also. No, I think I just copied that then.
Okay. Oops. Oops, sorry. I think then we want to pull this second half out and say remainder equals. And then for all these, we need to say as instance of A for now. We need some quotes there. All right, some car dot as instance of A. All right. Okay.
So now this flat map one here, this is where things start to get interesting. And we've got a little bit of a choice here, because what this is really saying do is run this parser, and then once we're done, then use its result and run this other parser that we're going to get from this F thing here. And so there are two broad ways we could do that. So the simplest way is just going to be run the first parser, get its result, and then run the second parser. So that would look something like, I could say val result is equal to parser dot parse. And so here's where, if we really wanted this, so this is going to parse the remainder. And when we're done with this, it will have transformed the remainder by actually changing its value. So then if we wanted to, we then should be able to say something like new parser is equal to f of result. Oh, right, we have to, so we have to match on the result, because we may have, or we can just match on it. No. Yeah, there you go, perfect. So if it's none, then we'll just have none here, and we could probably change this into a map, but just for kind of simplicity here, we won't right now. And if we actually got a value from the first parser, then we're going to use that value to get a new parser.
I think here's potentially where
we're going to need to do some casting, I think.
I don't know if I can cast it as A though either, because
I think you can cast the function as a function from any to parser.
Yep, since that's fun. Parser, lovely, of I guess B in that case, or A.
Oh yeah, or we don't have a B. Yeah, this is where sometimes it can be helpful to just forget all the types internally here. And then once we have the new parser, then we can do new parser dot parse remainder.
One thing, so will this remainder be changed by this parse function though? Because isn't this parse function going to basically jump us back to the top and create a new remainder with the given inputs? I don't know if it's going to actually, like, we're not passing down a reference to our remainder to this parse function. So I'm skeptical that, I could be wrong, but something.
Well, here, so this remainder is this one up here, right? On line 14, which is a var. So parser dot parse, whichever one we're doing here. Oh, right. Yeah. So I think this is kind of getting us to, so we have that issue, and we also have an issue where we have a stack safety problem here, because every time we do this, we're going to be building up, every time we do this, we build up an additional stack frame. So this is not going to be stack safe as we've done it here. So I think this is where we probably want to move to more of kind of the full version of what this looks like, where we actually create a loop here, and we'll just kind of continually do this in a loop here.
Yeah,
does that make sense?
If we kept the same signature, I think it would have worked, but it would have been basically the same exact idea, except flattened to a single method. Like if we got both the value and the remainder, okay.
And the remainder, exactly.
Remainder long.
Exactly.
But yeah, we're sort of like in between worlds right now.
Yep. Okay, so for this then, we're going to want to get a little bit more complicated here. And we're going to want to maintain some additional state here. So I think we're going to want to maintain some concept of the current parser. And we're going to want to have a stack. And I think we can do scout. Beautiful.
Nice.
Okay, so this is going to represent the current parser that we're working with. And this is going to represent any continuations of future parsers that we're going to need to run based on the results of this parser. And so then we can probably just have a loop here. And we can say, let's give ourselves another variable here of whether we want to keep going. And so while we're looping, we're going to match on the current parser. And so now let's think about the implementation of each of these things. So now if we're succeeding with an A, we need to ask ourselves a little more than we did before, because we need to know that either we're done, there's nothing else in the stack, in which case this is our result, or we need to actually get the next thing in the stack and we need to feed our result to that. So we can either, yeah, we can either just do that here. Sometimes it's helpful to pull it out in another method, but I think probably here it's just simple to do it in line. And if you watched our Zero from Scratch series, you'll probably be noticing there are some like significant like similarities here of, we have a similar concept of an interpretation loop, similar concept of a stack, and not that you always need a stack. This is necessary if you want stack safety. We don't necessarily need to have that. There are actually some trade-offs in implementing parsers of like, do you want to be stack safe because you can be faster if you're not? But right now we'll follow a similar pattern. So we'll say, okay, if the stack's empty, then we succeeded. We're done. There's nothing else to do. Just return the value. If the stack's not empty, then we can say the next continuation we need, we can get by popping one off the stack. And then we can say, oh, and we need to say loop equals false there.
Yeah, and I think we probably need
and we need a value for our results.
A result, right, which is going to be of type A always, which can start out as null, I suppose. Or rather, it's going to be an option of A. So I guess we could set it as none, even though.
Yeah, I think that's probably good. Yeah.
There, but yes. Okay, so then we can say result is sum of A. And then here we'll need to say as instance of A. And this we can, I think, pull out, as you're mentioning. I'll just pull this into a local path.
Okay, perfect.
That's just called done. Or yeah, done. Okay, cool. Which will just do all of that stuff and be a function of any to unit. So yeah,
just like actors.
Yes, you can see some of the downsides of this encoding, which is that there's some extra complexity, but that's for stack safety reasons mostly. And which, yeah, the other encoding just simply is not stack safe and really can't be, which could be a huge problem depending.
Okay, so let's think about this any car. So we're going to match on the remainder. And if we got a match, then we're going to pull off the tail. And then we can use that value we got. And we'll just call, yeah, exactly as it's done. We'll just call done here. And we'll see if this
case, actually, I probably do need to actually take the whole sum because we do want to finish it with the none case as well, potentially. So yeah, let me make these sum A. There we go. Okay, cool.
And then this can be right as instance of option A, I believe. And then here we need to match on it because at least right now we don't have a concept of recovering from failure. So we only want to do this in the success case, right?
Yeah, that's a good point. The current parser, yeah, is always going to take.
So I think maybe first we want to match on this, and we want to say if it's none, then we just immediately return none. And we
Hmm.
set loop equal to false.
Yeah, there is no current way of recovering from failure, given the current encoding. Yeah. Mhm. Yes.
Okay, so I think,
Yeah. So I'll do that here. So
Okay.
match. If it's sum, then we sort of want to do this whole thing.
exactly.
Value as instance of. Yeah, A is instance of this. Otherwise, if it's none, we just basically just do this case with results equals none. So yeah, definitely complicated. All right. Okay, and then for these, it's basically the same thing where we call done for each of these cases. And now, so it's kind of like an awkward translation of what we had previously, except instead of returning the value, we call this done thing, which stops our potentially infinite loop, and then sets the results to this thing, which we're eventually going to have to return at the bottom. We're going to return our results outside of the loop.
Yep. So let's see. So we're using done here. Okay, so now let's look at our flat map case. So now we can do this a little more, I think you could say, a clean way. So now what we can do for flat map is we'll just say current parser equals parser. What do we call it? Parser stack.
I think it might be stack actually.
Push F, and I think I'm going to need to do that as instance of to parser any.
Okay.
And then we'll just loop again. And now we'll start running that parser. And when it's done with whatever its value is, then we'll go to the stack and we'll get this one off of there.
Yeah. So I think what we have now might actually.
Yeah, there is also a little bit of a scary aspect of this, of like the executable encoding, like each step you do and it kind of, okay, it works, and you build it up. Like here, like there's a little bit of like, okay, we were like implemented the interpreter, let's see if this thing actually does what we want, or if we've created some terrible thing in here.
Yep. That's fun.
So let's
so I
see.
think
Yeah, do we have?
we do need an int parser first, by the way, but I think the way to do this is actually to implement one more maybe fundamental operator, which could be map or fail, which could basically be.
Yeah, or can't we just add fail as a new primitive?
I think fail is good, which would basically just be a parser of nothing. Yeah. And it would, yeah, exactly.
Right, yeah. So another thing, I mean, we're kind of doing this partly just to illustrate, but you could think of the parser as having like a string or something else for the error type, and then fail would actually have information about that. But right now, since we don't have that, fail will just extend parser of nothing.
Okay, so I'll go up here at the very top, or maybe after succeed and do parser dot fail, and it'll be the opposite, right? Where we are going to call this done method with none.
Mm-hmm.
So potentially now we have enough primitives to, is everything happy? I thought I saw red. No. Okay, so now basically we want to parse any car, and then we can flat map. And so this is nice because we get the car, and we could say car dot to string. By the way, don't just do to int ever on a car, because it will get you the ASCII code for the car, which can be confusing if you're trying to parse out 7. It'll work. It'll just parse it out as 57 or something like this. So you want to make sure you do to string first, and then in our case to int option, because we want it to fail. And then if we get the int back, then we can call succeed, or yeah, parser. Oh, we have succeed down there, so we could succeed with the int. Otherwise, we can fail. And there is no fail, so we'll create a value called fail, which will be a parser of nothing, and it'll simply nothing, and it will be our fail parser. So this is kind of, yeah, now we have the ability to do this kind of map successfully or fail, which is nice. And now we should be able to actually run this example. I hope. Let's see what happens. I'm going to run the executable version or the declarative version now. Okay, no, totally something blew up. That's great. Some cannot be cast to character. So on 130, that's fun. So some could not be cast to car. So it looks like calling this continuation got us something, which was a sum. Let me print out here, print line, and I will call continuation of A. And I will also take a look at what A is in this case. So A, cont. We'll see what blew up.
Oh, well, hold on. We're our sum here is not, this needs to be A, right?
Oh, sorry, what?
Oh.
What? Let me jump to you. My bad.
So we had this, right?
Oh, yeah, duh.
Right, so I think we need that.
So yeah, this is the option of A, and then that needs to be the A, but I do think why I kept it was silly because of this reason. Option of A we want to keep here, and then not there. So yeah, totally. Duh.
We may still pull up for another reason momentarily.
Yes. No. Okay. Well, now we got none, which is not ideal because it shouldn't have been none. So let's try to debug a little bit. That's exciting. So I'm going to make a new version that's our simpler parser. So I'll do parser.int, parse of just a number. Like, will this work? I'm guessing no, but we'll see. No. Okay, that worked. So that worked. So there must be something maybe with the flat map or something else. So flat map could be the trick. But one of the cool things about this is that it's really easy to, well, it's not really easy to debug, but we can debug it because basically we can print line here at every step of the way and see sort of our current parser is what? We can do current parser. What is our stack? Take a look at the stack. Should we keep looping? Loop, etc. Do we have a result? Result. Oh, and of course the remainder. So we could see if something has gone horribly wrong. So let's see where. Maybe I should add some spaces. Oh no, because we barely made it anywhere. So that's great. So the remainder was the whole thing. We called flat map, and then okay. So there's a problem with maybe flat maps interpretation, which would make sense. Yeah, because we're never calling anything. We're changing that. Oh yeah, because I'm only doing it at the top. I need to do this inside of the loop. I did it too early. So inside of our while loop, which, there we go. Okay. So let me try that again. Okay, so we did do a bunch of stuff. So let me make this way bigger. So we started out with flat map. Then we moved ourselves down to the car parser inside of the flat map, which we did not consume any input yet, which makes sense. And then we consumed our car parser of opening parenthesis, and we got, it's kind of nice. We can simulate what's going on here. We removed one piece of our remainder. And then we got into this flat map any car, which is for our int. This is basically what our int parser turns into, I believe. So flat map, we're moving closer into there. Finally, we get the any car, and we have something on our stack, two things on our stack, right? One is which is going to call toInt on the thing. So we called that in there. Our current parser is now succeed of 8, so that totally worked. We got an 8 out, and then we continued along, which changed our current. So we called this with our 8, which got us this, the next parser, comma space, which gets which will parse out this, and then the continuation is going to parse out hopefully the int, and then continue from there. So no, okay, so our string parser failed, so that's good.
Oh, okay.
The string parser did not do what it should. So that's great. There's probably something obvious there.
Oh, this needs to be a remainder.
Okay, amazing. All right. So not the worst debugging experience. And yay, now we get a chord. So
Nice.
and we can now have this cool debugger that we can use or not use as we see fit. So yeah, that was fun. Probably a little less elegant of a transition than it could have been. In full honesty, we thought we would just pull this example out of our heads on the fly. Maybe a little bit of hubris.
I think we added stack safety at the same time we shifted to the declarative encoding, and I think we could have, like you said, kind of passed through the state and then kind of moved to this. So we had a little bit of two things at once, but still in like roughly an hour, we've done two different encodings of this thing. So that is pretty cool.
Yeah,
and you can see here. Oh, sorry, go ahead.
No, you go.
Oh, well, I was just gonna say, you can see here how we created an API here that was a little bit more flexible for us as implementers, because in the executable one, we had our parse method returning that A in the string. So we were kind of committing to this idea that the state that we're maintaining is a string, and every time we do something, we return a new string. Versus in this new one, that's completely internal to our implementation of this parse method. So if we wanted to change that from being, well, we'll return new strings to we'll just change like an index into the string, or maybe we'll maintain like a chunk of characters and we'll just index into that, or even like an array, like any of those things we could do, and it would be purely internal to this implementation. And you can also see how we had all the state in here. And just like when we did the Zio from scratch series, we've got the ability to add whatever additional state we want in here to keep track of other things, like, are we supposed to be actually consuming these characters and doing something with them, or are we just discarding them? Or any other information that we need to maintain as we're going through and we're parsing this thing.
Mm-hmm. Yeah, and then we have our other sort of version at the bottom, which we could write in some other way. So I mean, if we wanted to, we could do that version that we were sort of looking at before. I mean, so yeah, that's actually kind of interesting. I'm at the bottom here. So if we did want to make that intermediate version, we could basically have ourselves a parse impl that could take almost the same stuff, parse sort of a string, and then it could return, this method can return both our option of A and a tuple of option of A and the string, right? And this is just a different implementation that we have in here. So we could do this, do libd, write the right methods correctly and whatnot. Anyway, have this be a helper or something, right? And just as it was sort of in that other version, but it could be totally sort of hidden out from here. So we could write a method that interprets it with that extra remainder being funneled around, and then hide it from here and call whatever parse impl with the parser with the string, and then map over that again in a similar way. So we could do both. We could have our stack safe version and our stack unsafe version that will in here sort of recursively call parse impl with each nested parser. So basically the implementation of flat map down here would call parse impl on the result of parser and the string, and then it would match on this result, getting back the partial results, value and remainder. And now we can call this f with the value, and then we can call parse, not parse, but parse impl on this with the second remainder. So we can thread that stuff around, and we have to obviously fake everything that we need, or whatever. I think I need to once again change this thing. So the biggest downside, I think, to declarative encoding is that Scala gets a little confused around the types, and you end up having to erase a lot of these parameterized types and just say lots of things are of any. So I need to make this a function from any to parser of any, and then we're good. Or maybe to parser of A or whatever. and then we're good. And this could just be none at that point. And we can, these implementations, we could more directly copy over from the executable encoding. So this would be sort of the non-stack safe version that is just having all of your stuff in one file. We don't need that var for remainder or anything. So maybe this would be a simpler intermediary. But now we have the power to implement the full stack safe parser, which is a huge benefit if you need it, right? If you need stack safety, you can't not have stack safety. And maybe parsers don't always need stack safety. I mean, probably don't, parsing a huge thing. There might be some other tricks you can do, but in some domains, this is sort of a general technique that could work for anything, any sort of program or domain-specific language you're writing, to use both the executable encoding and the declarative encoding, which lets you really put a lot of horsepower on the thing and have a lot of flexibility. There are a couple questions.
Yeah, let's do it. Let's see.
So correct me if I'm wrong, but it looks like, so this question is from Andre. Correct me if I'm wrong, but it looks like the whole point of a declarative encoding here is to have control over execution without actually leaking this process to the API user. In other words, clean but composable at the same time.
That's a pretty darn good description. Yeah, I think it's the idea of getting all the state in one place and maintaining the state internally. So yeah, if you really wanted to, you can always take whatever that state is and pass it around between all these things. But one, there could just be a lot of it by the end of the day. And yeah, it kind of leaks into what you're providing your users. So I think that's a really good description.
One other benefit that's pretty big, and I don't know if our DSL is, well, first of all, it's not minimal because there are certain things that we could basically erase any car and car parser and all these things. Car parser could probably be done between FlatMap and any car. So like this set could probably be more minimal, but that's totally fine. But one other big benefit is that we're now able to introspect on our DSL. As we mentioned before, like we can't call, you can't call self.match. We're going to get like this. All we know is that it's a parser, which we already knew. So that's basically, there's nothing we can do there. Here, we were able to sort of create a language and some primitives, and we can introspect those primitives up to a function boundary. So beyond FlatMap, we're kind of screwed. We cannot introspect what happens after this computation, up front at least. But there are many potential operators and optimizations we could do before reaching that function boundary. And it depends on your DSL. I think we looked at an example of this in maybe Zio from scratch, where we sort of calculated the number of steps that we were taking with our Zio effects.
Yeah.
It may have been before FlatMap.
Yeah, well, one of the things that could be interesting to do maybe in one of these follow-up sessions is look at a parser that actually doesn't have that as an operator at all. So there are some types of grammars where you need that equivalent, the power of FlatMap to kind of dynamically decide what you're going to parse next. But you can actually parse a surprising number of things without using that at all. And it's actually often more performant to do it. So like it was very easy to go to that like for comprehension we had at the beginning when we're doing the parsing. But that's probably, if we want to be efficient, even if we had the power to do that, we actually wouldn't want to use that operator. And we can create parsers that are more introspectable if we don't have that. So it could be interesting. We could do another session where we like take one of these, maybe we start with the declarative one and we do like another version of that doesn't have that. And we add some other primitives and we see like how far we can get with that world.
That does remind me, there is one optimization that I have, which would be sort of the or else primitive here, which would take sort of two parsers, right? A left-hand side parser of A and then a right-hand side parser of A. And this would try to parse the left-hand side, and if it failed, it would try to parse the right-hand side. Now, you could imagine we could, if we wanted to, like have a method called, say, I don't know, optimize. which would take whatever our parser is and just return the same type of parser, but doing some potential things on it. So we could match over our structure and we could see, okay, wait, if we could look at for particular patterns, right? We could look for if they're both car parsers, for instance, of car1 and car parser of car2, right? And then if we had maybe another primitive called parser.like bit set or something, we could create a bit set from these two parsers. And this would be maybe a parser of characters, but that one that would just sort of very efficiently match many characters against a single character in the input at once. And we can optimize, like the user can still write their API in this nice high level, but we can do an optimization pass where we simplify particular cases or remove branches that don't make any sense. That's a huge superpower that you do not have at all in the world of executable parsers, where you just, it's a parser, that's all I know. That's all I know. So let me get rid of all that, but that's one example. Then there are two questions from Phil Allen. So the first one is, how could you make the continuations properly typed? I think this is also a question that came up during the Zio implementation, Zio from Scratch series, which the answer is basically, well, maybe it's possible if you like store some huge heterogeneous list as the type of the parser. But the problem really is that every time we're calling flat map here, we are nesting another level deeper, right? If we desugar this for comprehension, we're flat mapping again and again and again every time we have one of those binding arrows. And each of these intermediate types, like first we have a car, then we have an int, then we have a string. These are all different types. So if we wanted to preserve that up here, we would need to like have some huge H list. And I'm still not even sure if that would really help us implement this, because we couldn't just have a type. All we know at this level where we're implementing it is that there's some type. Imagine if there's some like big H list type. Well, we still don't know what values are inside of this. So the best we could do is maybe like it can give us a little safety to make sure that we've like pulled off a value in particular places, but I'm not even sure if that's possible. Sometimes when you just get this dynamic or something, like it's hard to maintain that sort of type safety over a series of continuations, because the past is kind of obfuscated, or the future is obfuscated behind these function boundaries. And it may not help us implement the interpreter. Something like that might help you implement, like in userland code, certain things, or know certain things about the type of parser you were building for certain optimizations or whatever. But I don't think at the interpreter level, any of that would exist anymore.
Yeah, I think there's probably a way to do it, but I think it has some performance costs. There's not really a benefit to doing it to justify it in a case like this, where it's going to be used internally in just your execution. There are other cases where doing very advanced type level machinery makes sense. So like if you want to check out Zio SQL, like there's a lot of like work and thought that got put into preserving type information and building up the right way so that you have this like type safe way of building like a SQL query. But here there's just not a payoff for doing that.
Even there though, I'm not sure, does that type safety help in like the interpretation of it, or is that mostly like
no it's just so that in user land, when you build things, it has that type safety.
Mm-hmm. So yeah, you know precisely, the shape of the queries that you're making, and you can match on them and whatnot. So
if your program is running too quickly, you can solve your problem by throwing in a state monad there. That will definitely help you out.
So to read the question, which was the second question, was would you gain anything by replacing mutable state with state monad fanciness? And in this case, yeah, probably no, right? Because state monad mutability is always going to be faster. The problem is mutability isn't always as understandable, but I don't think a state monad at this level or anything resembling a state monad would give us much. I mean, this interpretation loop is kind of low level, and it's sort of nice to have that property.
Yeah, and I mean, one other thing you can think of there is a lot of the mutability here is actually maybe convenient, but not strictly necessary. Remember, anywhere you have a while loop, you could always rewrite it as a recursive function. So if we wanted to, we could have some def loop here that has state and is tail rec on it. And every time we would otherwise kind of loop here with the while loop, we just call that loop function recursively and we pass through all the state. So we could make a lot of the state go away if we wanted to, but I think this is one of those cases where it kind of makes sense to call a spade, and like, if we're gonna be doing all of this, essentially a imperative loop here, like, unless it has this like natural recursive structure, it can just be easier to just acknowledge it and treat it as the while loop it is, versus like trying to kind of put it back into that like functional world of like, okay, we'll just like call ourselves over and over again.
In fact, I'd say this is one of the biggest benefits of well, either encoding here, but designing functional DSLs, and I guess especially the declarative approach, which is that you can sort of define these in a very functional way, using combinators and so on, and just have these all be values. But in that safe little internal world where you're interpreting it, you can get as dirty and as fast and as hacky as you want. So you sort of get the best of both worlds, which is the speed of a mutable interface, a hacky low-level thing, which is all kind of constrained to hopefully like 100 or so lines of gnarly code that you can really sit down and meditate on and like fully absorb into your brain, fully saturate your mental RAM with all the little details you need. But then in the rest of the code, you get to work at a much higher level, trusting that minimal set of sort of orthogonal operators has been tested very thoroughly. And you can sort of just rely on those to sort of work. We're getting lots of questions today. This is awesome. I think
this is great. I know, this is really good. Yeah.
Questions that we've ever gotten. So Adrian has a couple of questions and then Phil's another question. So Adrian asks, does it make sense to have declarative encodings in general, not the parser domain, where the input is also parameterized? For example, well, I think what you mean then is, so if like parse also took some type of like, okay, parser inputs of A, and who knows what that's going to be, input of T. I mean, it's hard to imagine, well, it doesn't make sense in this case, right? But I think the answer could be totally, yeah, and I think so. Do you have any thoughts on that? I mean, it's probably be good if we come up with some specific examples, but I don't think that prevents it from working.
Yeah, well, 100%. So, I mean, one really practical example is Zio, right? I mean, Zio is, right, it's R comes in and E or A comes out, but obviously I could say, well, let me look at the Zio that can't fail, right? We look at the URIO, which takes an R and gives me an A. And that's exactly the signature of some maybe it's helpful to write it out here, the sum operation minus T plus R. And like the way you could think about that at like a somewhat conceptual level is that's the domain of function-like things, or I mean, if we wanted to get more theoretical of arrows, we could say. So this is something that somehow takes some input in and sends some input out. So that's like a pretty general thing. And then depending on exactly what that is, we could think of different declarative operations we could have here of, I mean, maybe a simple like word for this would be, it's a pipeline, right? It's a pipeline in out. And so you could imagine, well, if I have kind of two pipelines, I could put them together end to end so that the end of one goes into the beginning of the other. I could maybe do some type of like fan out where like I take that output and I like fan it out to like two different pipelines that are each going to do something with it. I could have some kind of like fan in where I have like two pipelines that like both produce a value and I like take the values from both of them and feed them into a new pipeline. So yeah, that could absolutely make sense as a language. And I think sometimes the thing to think about here is just the trade-off between generality and like domain specific knowledge of like, if we go super generic to just like, there's this pipeline thing, like there's definitely some like interesting things we can describe, but like it's pretty high level of like, you compose them, you fan them in, you fan them out, you do stuff like that. If you knew this was a particular thing, then you might have more operations you could define that would be more interesting, that would be specific to like your particular domain of like data transformation or whatever it is that you're doing.
Awesome. Oh, okay, and the follow-up. And is there some downside to that or cost to take into account? So I guess the answer would be no, because Zio does that exactly right. There's the R as the environment, and the A as the output. Sorry, I may have slightly interpreted the question.
Yeah, and I mean, I think that the downside would be any of these executable encodings. If you're not doing any optimizations, there's typically some performance cost to them of you're just like creating this interpretation loop. So like this pipeline thing, the simplest version of a pipeline is just a Scala function. And just applying a Scala function, right? Just being like, def x equals 1 + 1, feed in 1 is going to be faster than having some like pipeline interpreted data structure. Now, maybe the pipeline gives you other things if it's stack safe, or it gives you abilities to optimize that like more than make up for it, or maybe that ends up being a tiny performance cost relative to each of these describing some kind of thing where you're like loading databases or something. But that is one kind of downside to think about there.
Yep. And then I think our final question is from Phil Allen, which is, if you wanted to get decent parse error messages, for example, identify where the error may have started rather than just detected, what would you change? See if we wanted to get some error messages up in here. So, well, right now we're definitely missing a few bits, because we were kind of mixing this parsing domain. We didn't fully explore the domain of parsing. There's a lot else we could do, for instance, or else recovering from errors, having sort of typed, having typed error messages, but really just having sort of any kind of descriptive errors. We're just using none to represent that. Tracking the input position in here. We could definitely do that. Right now, we're sort of using this remainder, which we could also keep the input a string and just really track an offset or an index, which would be starting out at 0 and then kind of moving our way through the string. And we could recalculate the remainder based on what the index is. That might be faster anyway. But right now, where we're sort of returning a none when we're failing, right? We could basically just make, instead of returning, like the simplest way to do it would be to change this option of A everywhere to an either of string A, and have fail be parameterized by some kind of a message, right? So string message, case class, string message. And then, this would need a message, oopsie. And then up here, we could take that message and return that as sort of the left-hand side, or potentially have like a chunk of messages or a list of messages, a non-empty list of messages as the failure, and collect multiple messages in different cases. But I think that would sort of be the beginnings of it. Obviously, that gets a lot more complicated. Depends on what you want. Oh my goodness, we have so many questions today. This is amazing.
And just one thing to add on there, like I think that's another nice thing with like this interpretation loop is beyond like being able to have the user specified message. A lot of times you may want to have like what's like the line number, the column number where the error occurred at, and that once we modify the type to be like an either or something, so we have the type, the space to put it, then it's a lot easier to, whenever you're going through this interpretation loop and you find the error, we could just grab the line number or the column number, and that could be part of the rest of the state that we're maintaining.
What if I could do it really quickly? Right. None. Find every none. Change that to a left of message. Yeah, cool. Not quite. I think I broke some things. Oh wait, because it wouldn't be 2int option. That'd still be some int. That would still be none. But this fail would be a def, and then whatever message string message, and then we could say fail expected int, whatever, found car, right? We could like do that because we have what we found, and we know that we expected an int based on our parser. And then, oopsies, what does this need to be? Done would be, and now right or a left. Result would be that. Almost there. Oh, head option. Yes, some. I think this might almost work actually. And then message would be, oh, left did not match string. And then we could like even have the string right here that we expected it to match. And left message, done left, did not, oh yeah, input was empty. Input was empty. This is kind of like the final messages, and then left would be, oops, something went wrong there at the beginning. And then if we sort of broke our parser down here, because where we expected an int or something, we would change this to an x. Now we should see, theoretically, our message, if that was really fast, but oh, there, expected int.
Yeah.
Right, so there we go. Now we have error messages.
It would not be a live coding session with Kit if it did not have drama near the end.
I can't resist sometimes, so thank you for
That's true.
that question. Wow, yeah. All right, nice. And I think, well, we got one last question, so maybe we should keep it there, but oh my goodness, thank you so much, because we're just getting going a little beyond.
It's fantastic to get all the questions, yeah.
Yeah, so awesome. Please, if you have more questions that you want us to get to later, join the Discord and send them in the meetup channel there, and we will have to answer them after hours as well, or come back next week. And if this happens a lot, we'll do like a whole Q&A session, but so far we haven't gotten many questions these days.
I know, we tried that once, and that was, we had to improvise some content.
Which we can do. But anyway, so Tobias asks, I guess executable encoding is better when I need extensibility for adding additional primitives. Oh, I think maybe you need a mean declarative there. We've probably ourselves been messing up the definitions, as I do that all the time. I guess executable encoding is better when I need extensibility for adding additional primitives. Could both encodings be combined where a subproblem is declarative encoding that is interpreted to be an executive encoding, or is there a better way? Oh, well, that's actually a great point, which is that yes, you can go from declarative to executable. You can't really go from executable to declarative, because once you have, like, all you know about this, as we talked about, right? If you want to match on this, it's just an opaque parser. I mean, maybe if you add some extra properties to parser, like, you know, def name or something, and you're forced to implement that on every implementation, that could help you discern something about it, but it's going to be pretty hacky and weird. You probably just want to do a declarative parser at that point. But you can always make an interpreter, like down here. Notice how this version was different than our other version, right? This returned that remainder down here, but we can also have a parser, you know, execute. We can take our parser, and we can, instead of doing this, we can return an executable encoding, right? We can go from this to this. Yeah. And that's totally valid as well. So we could get ourselves back an executable encoding, or parse it into our other parser version, right? This could be executable.parser of A. We could totally do that, which is actually kind of interesting, right? This actually wouldn't be that hard at all, because we have, well, I don't know if we have executable.parser. Do we have have that .parser.succeed, right? Okay, so we can just kind of do this. I mean, there's no fail yet. So you can imagine that if we had the same combinators, we could translate, oh, then I wouldn't do this. We could translate our parser, our declarative parser, into our executable parser, which is pretty cool. But that's a one-way thing. It's, yeah, you can't go both ways.
Yeah, I mean, I think the other thing is, it's definitely right that the executable encoding is a little more flexible. Of, if you ever want to just add something else, you can just like go directly and create like a new primitive, even as user land, right? We could just extend parser, and we could implement that parse method, versus with the declarative encoding, there is a little more work to that, and to extend that sealed trade, and particularly if we want third parties to do that, that generally isn't going to work, because we need to, when we're interpreting, know all the cases. In practice, I find that that's less of an issue than you might think it would be, where I think that really typically just pushes you to have the right set of primitives that allow your users to do the things that you want them, that they want to be able to do. And sometimes the way you set those up can give you a lot of, or your users a lot of flexibility. So like if you think about Zio lets you embed any possible side effect in it. And that's true, even though there are only like less than 20 cases of the actual Zio primitives. And that's because it has a couple of them, like the succeed or effect one, that lets you just embed any arbitrary user code in there. And obviously, depending on your domain, there are trade-offs to providing that flexibility. But I would typically think about it as more of a challenge of like, how do you define those primitives so that your users can do the things you want, versus, well, I just need to open it up and kind of let them just define anything that they want to without having the structure of these primitives.
Yeah, kind of goes back to that idea of good pain, right? Like if your API is too flexible that allows anything, you know, maybe you don't really have much of an API at all, right? Or what's the design there? Potentially, I mean, sometimes you need to do hacky things, but yeah, this forces you to think in a way that is good. Yeah, even still, this is not quite minimal yet, I'd say. Oh, okay. And I think this is a great final question, which is, do you publish Symposium code snippets? Symposium code, for example, snippets might be easier to go back over this stuff. Generally, we do. We should probably have a single repo where we do everything, but some projects are much larger. But lately, we've sort of been doing these things. So the Zio from Scratch series does have a repo that's, I think, on currently my GitHub, kitlangton/Zio from Scratch. And this one is not up yet, but I just made it, and I'll push it up as well. And I'll post this in the Discord. Or if you're not there yet and you're not joining the Discord, just feel free to, you know, follow me on GitHub, and it'll probably be up there in like 10 minutes.
Yeah. We could maybe even like create like a little organization or something, so we could have different repositories under it and it could all be in one place.
Yeah, that would be great. Yeah, these Symposium or whatever, Zio Learning, iVerge Learning, something or other.
Yeah.
We'll get it out. That's a great idea.
We'll see. Usually at least one advantage of the Z is that it helps avoid name conflicts.
Exactly. But thank you so much.
Right.
That was
thank you so much, everyone.
Great. I feel seen.
Yeah, love the questions.
Yeah. We'll see you next week. Thanks everybody who asked questions and everyone who just stood by and joined us. And yeah, appreciate it. It was super fun.